In this video, I'm going to show you how to do a very famous calculation in quantum field theory, one that you almost definitely will do in any introductory quantum field theory class, where you will almost definitely deal with quantum electrodynamics for the first time, and it is the calculation of the scattering cross-section for tree-level pair annihilation. It's one of the classic calculations in quantum electrodynamics and quantum field theory generally, and in this video I'm going to show you how to do it from scratch in full detail. And by from scratch I mean starting with the Feynman rules. As I mentioned in the video, if you want to know how to derive the Feynman rules themselves, I also have a video on that, link in the description. And beyond that, by from scratch, I guess I also mean the general differential scattering cross-section formula for the case of two fermions scattering to an arbitrary number of bosons. If you want to know how to derive that formula, as I also tell you in the math section introduction, there's a link to that in the description too. Beyond this, I'm not going to tell you much here. Let's just dive straight into the math section itself. Let's get going with this derivation of the pair annihilation scattering cross-section at the tree level in quantum electrodynamics. In the treatment of quantum electrodynamics in introductory quantum field theory courses, once the general scattering cross-section formula has been derived and the QED Feynman rules have been derived, one usually moves on to tree-level QED scattering cross-section calculations. This usually represents the student's first time applying the Feynman rules of any theory and is intended to be a reasonably handleable mathematical endeavor. Of course, it's still quantum field theory, so it's inevitably going to be a little crazy, but comparatively it's more manageable than a lot of the math that shows up in QFT. One of the first in this set of cross-sections that students usually calculate is the differential scattering cross-section of tree-level pair annihilation. For those who don't remember, this is the process where an electron and a positron annihilate to yield a pair of photons. This is the scattering cross-section first calculated by Dirac that we will be deriving in this video. Of course, one could always expand on the tree level with loop diagrams, but this is significantly more complicated. It isn't usually done until long after students have computed the tree level result. The tree level result in calculations like this just reproduces the classical answer, despite the fact that we are using quantum field theory machinery to compute it. One only gets quantum corrections from perturbative quantum field theory if loops are included. The expansion in the number of loops is also an expansion in powers of Planck's constant, and therefore represents an expansion of the quantum corrections. Ignoring them would therefore naturally just leave us with the classical result. In the case of pair annihilation, this division between classical and quantum is a subtle point because one usually hears of antimatter as a consequence of applying relativity to quantum mechanics. The resolution to this confusion is the following. In mechanics, this is how antimatter works. Antimatter is a consequence of applying relativity to quantum mechanics, but in field theory, things are slightly different. In field theory, the Dirac equation, Klein-Gordon equation, Morita-Schwinger equation, etc., just relativistic wave equations in general, which play the role of relativistic quantum wave equations in mechanics, are reinterpreted as classical field equations, and then one incorporates quantum theory by quantizing the classical field and using the quantized field theory to calculate the effects of quantum fluctuations in the field. In field theory, therefore, antimatter is a relevant concept even at the classical level. Specifically, the relativistic quantum wave equations that give rise to it are taken as the classical field equations of the various relativistic particles, and that's how it gets into the classical level. With the preamble done, let's now get to the actual calculation. At the tree level, we have these two diagrams for pair annihilation and QED. The rules for getting these are that you must write out all topologically distinct diagrams that include no more than the allowed vertices, and if you're doing the tree level, you must also exclude loops, which just reduces us down to these. As usual, solid lines are fermion lines and wavy lines are photon lines. More specifically, the solid lines are electrons if they have a forward in time arrow, and positrons if they have a backwards in time arrow. And there's no distinction for internal lines, they just get a fermion propagator regardless. Ignoring the ones that pertain to quantum loop corrections, the QED Feynman rules are given here, where the dot product of the polarization vectors for the photons with themselves is just equal to -1, as usual. If this table of Feynman rules is mysterious to you, then you can take a look in the description where I have a link to a video where I have derived the Feynman rules for quantum electrodynamics. Expressed in terms of the Feynman amplitude, the general formula for the differential scattering cross-section of two fermions producing some number of bosons is this. Now, if this formula also looks mysterious to you, then I've got another video linked to in the description where I show you how to derive that. This calculation will have a few distinct stages. First, we will simplify the general differential scattering cross-section formula as much as we can without knowing the Feynman amplitude. Second, we will use the Feynman rules to write out the Feynman amplitude, and then we will simplify it some. Third, we will take the absolute square of the Feynman amplitude and then spend the largest single portion of this document simplifying it. At the very end, we will insert the simplified squared Feynman amplitude into the pre-simplified differential scattering cross-section formula. With a little more simplification, we can obtain the final answer. The first thing we will do in this section is insert the momentum variables written in the Feynman diagrams into the differential scattering cross-section. This will begin simplifying it because we can see from the diagrams that there are only two outgoing particles and the incoming particles have equal mass. Scrolling back up to those diagrams, we see not only that I've labeled all the variables, including the polarization vectors for the photons, but we can also see, as I said, there are two outgoing particles and both of the incoming particles have equal mass because they're antiparticles of each other. Plugging that into this formula gets us to this formula. At least it does if we do one more thing concerning the Feynman amplitude. Beyond this, the standard result also includes averaging over the incoming electron spins, so we will need to insert the average on the absolute squared Feynman amplitude into the differential scattering cross-section. So all of those things gets us to here. You may notice that I added a 6th superscript to the differential on sigma. This is to indicate how many differentials there are on the other side of the equation. This number will drop as we complete phase space integrations over some of the momentum and energy variables. Specifically, because we'll be integrating over some of these, there will be fewer differentials on this side, so this number will drop. The normal convention is to not have a superscript on this side at all, but when I do that throughout the whole calculation, it sort of makes it look like d sigma is equal to a bunch of technically not the same things. It's already different from up here because we're specifying that there are only 6 differentials on this side instead of 3 times nb. Now it'll drop further as we do the phase space integrations, as I just said, and then at the end there will be a 2 left over because we're doing it with respect to the solid angle of one of the outgoing photons, as I'll talk about later. After this point, however, I'll drop that superscript, even though it's technically still a 2 and not a 1, because that's standard, and we'll be done with the integration at that point where the confusion associated with that is most likely. So once we've covered the part where confusion is most likely, I'll return to the more confusing standard notation. The scattering cross-section that Dirac originally derived, and the one that is most useful, is with respect to the solid angle of one of the outgoing photons. Therefore, one of the things we will need to do in preparing the differential scattering cross-section formula is integrate over the other momentum variables. It turns out that this can be done before we have worked out the Feynman amplitude because of the delta functions that show up in the cross-section formula. They are there to impose energy and momentum conservation. Therefore, we can do the necessary phase space integration without knowing the Feynman amplitude as long as we take the energy and momentum conservation relations to be true for the Feynman amplitude, which depends on them. It turns out that these relations are extremely useful in simplifying the absolute square of the Feynman amplitude. I chose to integrate over the k vector to begin with. This is the first step in getting the differential scattering cross-section with respect to the solid angle of the k1 photon. They're the same, I just made this decision between k1 and k2 arbitrarily. Of course, their polarizations are different, but that is not relevant to this. Because of the momentum conservation delta functions, integration simply yields this result, where we're left with one delta function and we're closer to getting a single solid angle differential there, though we've not quite gotten there. The delta function imposes this momentum conservation. To find the differential cross-section with respect to the solid angle, we must now put the remaining differential in spherical coordinates to reveal the solid angle differential. This contains 2 differentials, so we have a total of 3 on this side, even though it looks like we've only got 2 on this side. Now, to get the scattering cross-section purely with respect to the solid angle, we must integrate over the magnitude of k1. The remaining delta function allows this to be done easily, but there is a little complication. We must re-express the delta function to get it into a form that is easy to integrate over. Specifically, the integral that we need to perform is this one. Using normal delta function identities, we can rewrite this delta function like that, where this f prime function is the derivative of this argument of the delta function, which I've called the f function, and this k1 magnitude naught is the root of that f function, or the actual value of k1. Because of the delta function, the integral simply forces this relation to be true, relabeling the actual momentum k1 naught with the symbol previously used to represent the integration variable to make things simple, and then continuing the calculation gets us to this. If we actually look at the form of this f function here and take its derivative, we find this value for it. As I described above, the superscript on the differential is usually dropped. It was useful to keep track of things while we were doing the integration, but it is no longer needed, so we will drop it and return to the standard notation, which means we have this relation now. Keep in mind that because of the integrations that we did, d sigma doesn't quite mean what it did in the general formula in the introduction before any integrations had been done, even if we plug in the number of outgoing particles and end up with just the 6 differentials. We've reduced 6 differentials to 2 differentials. From here, the only way to simplify anything further is to select a specific parameterization for the momentum variables that respects conservation laws and the energy-momentum relation. The usual thing to do for this problem is to take the rest frame of the initial electron. This is what gives us the standard result. With that piece of information, we can then use kinematics and a bit of trigonometry to work out this parameterization. We can now work out what this f prime function is in terms of that parameterization, which is more useful to us. If we take this dot product with these values for the momentum vectors, we get this result, and therefore the f prime function has this value. Then we can insert it into the cross section, which gives us this. Then we get some cancellations right there, which reduces it down to this. Then we can calculate the magnitude of k1 in terms of this parameterization, which works out to be this. That squares this denominator quite conveniently, and we ultimately arrive here. Then we can do a couple other simplifications. First, we can calculate this dot product here in terms of that parameterization. It comes out really simply. That gets us here. Then we can factor out a factor of m, which cancels that m right there. And then we find that this just equals the magnitude of p, which gets us to this. Then we can divide the solid angle differential to the other side to get the final result for this, at least for this section. This formula has now been made specific to the problem and simplified as much as possible without knowing the Feynman amplitude. So now let's move on to figuring out the Feynman amplitude. The first step is to use the Feynman diagrams and rules from the introduction to write out the Feynman amplitude. There were 2 Feynman diagrams, so we have 2 terms in the Feynman amplitude. Using the Feynman rules to write them out gives us this. Then we can multiply the numerator and denominator of this fraction by the same thing, such that we get a difference of squares in the denominator to get this, and then we can perform the same process on this fraction. Now we can simplify down the denominators, specifically multiplying out this square gets us to this after we write it in index notation. Then for the terms where the vectors are the same, we can use this identity to replace them with dot products, which gets us here. This one just equals m squared, of course, which cancels that negative m squared, and then this one's just 0 because photons are massless. We can then rewrite this term in terms of an anti-commutator of gamma matrices like this, and then we can use the Clifford algebra satisfied by the gamma matrices to replace this anti-commutator with twice the metric, which then gets this to a dot product. Thus we've simplified this denominator down substantially. The second denominator simplifies down in exactly the same way to yield this dot product. We can then insert these back into the Feynman amplitude to get this expression for it. We can then begin simplifying down the numerator. This is the first numerator times the factor that it's multiplied by on the right, excluding the spinner. If we distribute this in, we first get that. Then we can reverse these 2 factors at the cost of a minus sign and 2 dot product terms using the Clifford algebra satisfied by the gamma matrices. That ultimately gives us this result for this numerator times that factor. Then we can actually prove that this dot product equals 0. Epsilon is the polarization vector of the photon it is dotted with, so it is transverse to this photon momentum vector, therefore their dot product is 0. Also, the goal is to write the cross-section in the rest frame of the electron, so the electron momentum only has a time component, thus its dot product with the polarization vector is also 0, and we get this. Then one can use the fact that the spinors satisfy the Dirac equation. The whole above term acts on a spinor in the complete expression. we have this as the original numerator we were simplifying applied to the spinner that it acts to in the full expression, and then after manipulations that we just did, we arrive at this result. However, because the spinner satisfies the Dirac equation, and this P1 slash here is a term in the Dirac equation and the mass is the other term, the signs work out such that we can just replace this with a mass, which causes this second term with this other mass to vanish, leaving just this first one, which is just this factor of K1 slash applied to the spinner there. Ultimately, this is the simplification we get. The second term in the Feynman amplitude simplifies down in a similar way to get this, where we have the same anti-commutation scheme going on. If we substitute this back into the Feynman amplitude, we ultimately arrive at this. We have now simplified the Feynman amplitude down about as much as can be usefully done at this point. The next step is to write down the absolute square of the amplitude and then simplify a lot more. Naturally, taking the absolute square of a quantity entails multiplying it by its complex conjugate. This raises a slight complication here, because that means that we must complex conjugate a complicated product of matrices. Luckily, there is an easy identity for that. First, we must reverse the sign of the factor of I at the beginning of the amplitude, and then we must reverse the order of the matrix factors. One can see what I mean by comparing the Feynman amplitude to its complex conjugate. That simple identity takes this to that. From these two expressions, we can write out the desired spin-averaged modulus squared amplitude. So using those results, we can express this like that. And then, because this quantity under the sum is a scalar, we can take the trace of it without changing anything. However, this is advantageous because now we can use the cyclic property of the trace to bring this factor over here, which then allows us to make use of these identities to rewrite these spinor factors, which are hard to deal with these easier to deal with factors. Substituting those in gets us to this, and then we can pull out these denominators, getting us to this. From here, we can distribute a little bit to get this result. And then from there, I've written it in terms of these T1 through T4, which are these traces here. I just took the trace numerators and gave them these fancy names so we can calculate them separately. Let's start by evaluating T1. This is T1, multiplying it out gives us this result, and then breaking up the trace into a sum of traces gets us to here. Next, we can recognize that traces of products of odd numbers of gamma matrices are 0, which gets rid of two terms, the ones linear and the mass, which gets us to this. The last term is 0 because of the middle factor, this right here. We can prove that this product actually equals 0 using the Dirac-Clifford algebra. We ultimately get a dot product of the photon momentum vector with itself, which is just 0 because photons are massless. That leaves us with this result for T1. Next, we can again consider the middle two factors, this P1 slash and the K1, and then we can use the Dirac-Clifford algebra to rewrite it like this. That turns it into this two-term thing. Again, we have this K1 slash K1 slash product, which equals 0, getting rid of this one. So now we've got a single trace with only 6 gamma matrix factors in it. Then we can reorder these two factors that show up in there, again with the Dirac-Clifford algebra. However, here it works out really nicely because due to transversality, this term goes to 0, so we just have that. So we can reorder these pretty much free of charge just by taking on a minus sign. Then we can also prove that these factors of the slashed polarization vector for the K1 photon just equals -1, given this dot product that I talked about in the introduction. Inserting this gets rid of that minus sign and two of the factors under this trace. Then we can manipulate this a little bit more. We can commute these factors at the cost of this term and a change of sign. Substituting that in gets us here. Next, we can prove that these two polarization factors slashed gives -1 also, which should be obvious because these two polarization vectors dotted with themselves are going to equal the same thing. Inserting that gets us this, and then we can use the Dirac-Clifford algebra to evaluate these traces of products of two gamma matrices. Doing that simply works out to be this. The 4 factor comes from the trace of the identity. Inserting that in gets us to here. We can then use energy/momentum conservation to prove a useful relationship for simplifying this further. Here is the energy-momentum conservation relation. If we do some subtraction and then dot this with epsilon2, and then remember that these two dot products are 0, we can ultimately prove this relation, which helps us simplify this thing down to that. We can then use energy and momentum conservation again with this subtracted version of the relation. We can square it to get this after simplification, which we can substitute into T1 to ultimately reduce it to this quantity here. Now, if you look at the original expressions for T1 and T4, you see that they're related by this interchange of momentum and polarization vectors. So we can easily get T4 simplified from T1 that's been simplified without having to go through all that calculation again, just by doing this interchange. Now, the second trace needs to be calculated. The second and third, by the way, are related by the same interchange, although they'll turn out to be invariant under that interchange and therefore equal, as you'll see. This is the trace 2, so let's calculate this. Energy and momentum conservation allows us to go from this to that, and then ultimately I broke this up into two terms, and I handled them separately. The first term is what we're going to start by calculating, multiplying all that out, and getting rid of terms that are zero, because traces of products of odd numbers of gamma matrices are zero, ultimately gets us to this. It gets rid of two of the terms. We can then use these two relations, which I can't remember if we proved them above. If I haven't proved it, then I'll just tell you the proof works the same as for the identities. Let's say you can reverse the factors of epsilon slash and its corresponding photon vector slashed with the cost of a minus sign. That dot product that would normally be there vanishes here because we're in the rest frame of the initial electron. So that's where those relations come from. We can therefore apply them to move this momentum vector all the way over to there, and then we can use a cyclic property of the trace to bring this over to the front right there. Now looking at the first three factors in the first term, so these, we can rewrite those using the Dirac-Clifford algebra first to get from here to this, and then we can distribute that out. Then we can use the Dirac-Clifford algebra as we've been doing to prove something about these consecutive products. In the case of the photon momentum vectors, these products just give zero, but here they give the mass squared, so we arrive at that. If we insert this in, then we arrive at this quantity here, but these two terms are identical but with opposite sign and cancel, so we get this. We can then use the cyclic property of the trace to get this p slash here to the front there, which gives us this. And then we can use these two relations again to rewrite this like that. Now we see that these two things, the two highlighted ones, both equal the first term. So we can take a half the sum of them equals the first term, and we can do some factoring to get this. And ultimately we can use the Dirac-Clifford algebra to simplify this anti-commutator of gamma matrices down to just a metric and a factor of 2, so which gets us here. Then we can apply this famous gamma matrix identity to rewrite it like this, and rewrite that in terms of dot products, and then we can simplify it because these two dot products are equal to -1, and we see we only need to do this second term trace. So let's get started with that. The terms linear and m have an odd number of gamma matrices, just like with the first term. They can therefore be ignored because they vanish, which gets us this result. Focusing on the last three factors, we can use this identity on them and the gamma matrix anti-commutation relation to get this result here. This one allowed us to reorder these factors at just the cost of a minus sign, and then this one we had to use the anti-commutation relation again, as we've done many times, to rewrite this factor and that one in the opposite order, not just at the cost of a minus sign there, but also this term. If we insert this in, then we get these three terms. We can then use these two identities that we proved above to simplify this thing down ultimately to this. The way that works is we use the cyclic property of the trace to bring this over here. Then we use this identity to reorder these two factors once this is over there. So it looks like this, and we get that sign reversal. But then this identity tells us that product is 0, so it simplifies down to this. Then we can use this identity to reduce this term down further to this. Then again we can use this identity to reverse these two factors to get this. And then we can use this identity, which is just that same classic application of the Dirac-Clifford algebra that I keep referring to in one context or another, in one form or another, to break up this term into these two terms. Then again we can apply this identity. It's really just a bunch of reapplications of the same identities over and over again until we finally get the trace simplified down to something we can do directly. But anyway, reapplying this to this term here, we get from here to here, again at the cost of a minus sign. Then we can apply this identity to this product here to get rid of this term entirely, and now we no longer have traces on a total of 8 gamma matrices. There are only terms with traces on up to 6, so we've made some serious progress. Then you may notice this product here, which we can simplify down with this identity to this term here, and then we can write it in index notation and apply this identity again. Inserting that here and then writing things as dot products gets us to this. Then, as we've used repeatedly now, we have that these dot products are 0, either because of transversality, or the fact that we're in the rest frame of the initial electron, and that simplifies this thing down to this, which we can then plug into T2, and we get this result for it. And then finally, we can get T3 by just doing this momentum interchange and polarization vector interchange, and that gives us this result. So now that we've calculated the 4 traces that show up in this spin-averaged squared Feynman amplitude, we can plug them in. This is the last formula we had for it. To get this, then we can cancel some terms that are easy to cancel and break up the fraction to take this form, and then combine some like terms, and then bring the fractions back together in a new configuration like this. Then we can use energy and momentum conservation to derive some new relations that are useful for simplifying this further. This is the energy-momentum conservation relation at the top of both of those. If we dot that relation on both sides of the equation with the 2 different polarization vectors in each of these 2 cases, and ignore terms that zero out because of transversality and the fact that we're in the rest frame of the electron, we ultimately get to these 2 relations, which allow us to make this term and this term equal, and this term and this term equal, so they cancel and we get this. Then taking the fact that we're in the rest frame of the initial electron again gets us from this to this. This is now simplified down completely, and we can insert it into the differential cross-section formula that we prepared earlier, this thing. If we insert our result that we just got here for this quantity in, we get this. Then we can rearrange these pre-factors sums so that they're a bit simpler, and rewrite it in terms of the fine structure constant. Doing that ultimately gets us down to this. There we go. That is the differential scattering cross-section for tree-level para-annihilation in quantum electrodynamics. It is the standard result that Dirac derived. It's done in the standard reference frame and with standard notation. That is how you derive it directly from quantum field theory. So now you know how to derive the differential scattering cross-section with respect to the solid angle of one of the outgoing photons for tree-level para-annihilation in quantum electrodynamics. I hope you found this video fun. I hope it was educational, but mostly I hope it was fun. This kind of mathematical physics is, after all, objectively fun. But anyway, if you liked my video on it, please give it a thumbs up, and don't forget to subscribe. Dietrich out.